Thanks, everybody. Today's video is going to be about chaotic pseudo-random bit generators. Okay, so I'm going to present to you some results from a recent publication. It was published on IEEE Access, and it was a very recent publication. The title is Testing the Strength of Chaotic Systems as Seeds in Pseudo-Random Bit Generators. So the basic idea is how different chaotic systems behave when they are used in a specific prbg. Now, as you probably know, I have many videos in my channel. We focus a lot of our work on chaotic encryption. Okay. The idea behind chaotic encryption, let me explain very fast, is that we are using some sort of chaotic source, probably a discrete time chaotic system, to hide some information. This can be image, text, or a video. Okay. And there are very standard operations that can be performed using chaotic systems. For example, the standard actions of permutation, shuffling, and substitution, which is replacing the bytes or the um, bits in the information text or the information file. Okay, then we safely transmit this information. And here we're using the fact that chaotic systems are deterministic. So the whole encryption process is reversible. So once the receiver takes the shuffled or encrypted information, they can practically reverse the whole encryption process in order to obtain the original file back. Okay. Oh, so this is why we are calling this symmetric encryption. Okay. And for symmetric encryption, basically, you need at some part of the design a chaotic pseudo-random bit generator. Okay. You are going to use it probably during the shuffling stage or probably during the substitution stage. But I dare you, if you go to Google Scholar and search for chaotic encryption, you are going to find a lot of papers, and probably 99% of them are going to use a chaotic prbg, a pseudo-random bit generator, to perform the encryption. Okay. So prbgs are very, very trending in chaos-based encryption, and also they are very trending and relevant in other applications of chaos. So it doesn't have to be encryption. It may be path planning. It may be watermarking, authentication. So other applications relevant to security, optimization, whatever. Other applications relevant to security actually use chaotic PRBGs. Okay. So the idea behind the PRBG is this. Okay, let me explain. I'm going to move my camera up and down so that you can see everything. Okay. So the idea is that we are starting from a set of keys. And when I say keys, I'm practically referring to the initial condition for the chaotic system and the parameter values for the chaotic systems. These are the keys. Okay, so once we have the keys, we simulate our chaotic system and obtain a chaotic time series. Okay, and then we are going to use this chaotic time series and pass it through a function which is called a hash function. And this hash function is going to give us a fixed length output in each iteration. For example, it may give us, through some processing, a bit per iteration, a 0 or a 1, okay? Or a byte in each iteration, okay? Which is a number between 0 and 255, which of course is equivalent to 8 bits, okay? And by that, I mean that in each iteration, we always know that we are going to have a fixed number of bits in the output, okay? So this is a pseudo-random bit generator. By the way, some works use pseudo-random number generators, but the idea is basically they are equivalent, okay? Because you can take, batches of bits and transform them into an integer. So basically, PRBG and PRNG are practically the same, okay? So here, when designing the chaotic PRBG, there are several aspects that must be satisfied in order to have an actually really, really good PRBG. Okay, so you may find a lot of PRBGs in practice. Not all of them are equally good. Some are very good. And in order to have a good and efficient PRBG, you need to have some specifications. First of all, regarding the keys, you need to have a high key space. By that, I mean that, every time we change the initial condition for a chaotic system, we obtain a different solution. Every time we change a parameter in the chaotic system, we obtain a different solution. Okay, so the whole number of possible different solutions that we are going to get has to do with how many different key values we can choose. Okay, so the number of possible different conditions, different solutions that we can obtain constitutes the size of the key space. Okay, So, since we are using chaotic PRBGs mainly in encryption and in security in general, our key space needs to be high in order to resist the so-called brute force attacks, where someone doesn't know the keys, but simply considers a very big for loop and tries again and again and again sequentially different keys until he finds the correct one. Okay. If our key space is very, very large, doing this simple for loop will fail because it will simply take a lot of years in order to find the correct keys. So the key space needs to be high, needs to be very high. Second thing is that the chaotic system that we're using and also the hash function we're using has to be specifically to some extent lightweight. Because if you think about it, you might say, Lazarus, come on, we can define our own chaotic system. Just take some, sine, compose it with cosine, and then take the exponential, and then take the modulo of this and pass it through a second sine, and then take the logarithm, and then the modulo, and then pass it to an exponential and sine and trigonometric function. Okay, will this be secure? I don't know, maybe it will be, but we're introducing so many operations. What are we doing here? We're going to make an prbg that may be statistically random, but it's totally inefficient. Who the hell is going to use a prbg that takes 10 seconds to generate a million bits? Okay, nobody's going to use that. It's super impractical. So we need to keep in mind practicality. Okay, we need to define a chaotic system and a hash function that is complex enough, but also lightweight. And this is a very big problem because many publications in practice, they don't necessarily follow that rule. Okay, so this is a very big and important specification. Of course, another specification is the fact that the hash function that we're using needs to somehow hide the relation between the input chaotic map and the output bits. Okay, why is this important? Well, it is important because basically in chaotic encryption, there is going to be an adversary that tries to steal some information from you. And by steal, maybe, they are trying to observe a number of bits in the output. And by observing the number of bits, they may be trying to, say, for example, guess what are the actual underlying values of the map. Okay, so we need to define a hash function here that blocks this relation, that it is highly nonlinear and also non-invertible. So if someone observes the output of the prbg, they cannot guess what is the underlying value of the chaotic map. Let me give you a very simple example of a bad prbg. Okay, let's say we have the logistic map, very well-known map. It gives values between 0 and 1. Okay, and I take this threshold in each iteration of the chaotic logistic map. If the output is larger than 0.5, I have a bit of equals 1. And if the value of the chaotic map is lower than 0.5, the output bit is 0. Okay, so basically we have a super fast hash. The hash is a very simple threshold comparison. It's extremely fast, it's extremely lightweight, but it is not secure. You may think why? Well, basically, each output bit gives us information about the underlying interval of the map. So if I have as an output 1, 1, 0, I know that for 3 consecutive values of the map, I have the first value higher than 0.5, the second value higher than 0.5, the third value lower than 0.5. Okay. You may think that this is not information, this is not an important information, but actually this is very important information because if you give me a couple more values from the prbg, I can actually guess what is the underlying value of the map. Okay, so this sounds like a super fast and very nice and efficient hash function, but actually it is extremely insecure, especially if we are using very simple maps like the logistic map. Okay, so the relation between the map's value and the output bits must be hidden. Okay. And of course, after we do all that, above all else, this is called a pseudo random bit generator. Okay. We call it pseudo because we are using a deterministic map. But the randomness means that the output should be statistically similar to white noise, to a random series. Okay. So we need to have that above else because that's in the title. It's prbg. Okay. So the randomness needs to be satisfied. This is usually tested by considering 15 statistical tests, the very well-known NIST statistical test package. Okay, and we definitely need to satisfy that. Okay. So what's the problem here? All this sounds fine, and of course, there's a very big actual research agenda going on at the moment about addressing these issues. So the thing is this, if you go to Google Scholar and search for chaotic encryption or chaotic prbgs, you are going to find many, many papers for this specific topic, okay? But what's the problem? Uh, each paper in the literature has its own prbg, which of course uses a collection of, I say, 5 to 10 very standardized rules. For example, the rem operator, the modulo operator. There are some very basic hash functions, like the comparison operator I mentioned earlier. So there are a couple of very specific hash functions that are used, and there are several variations of them. So each paper has its own variation of a PRBG. Okay, and also each paper uses its own chaotic map. Okay, so you will see in the literature, 10, 20, 50, 100 different papers on chaotic PRBGs or chaotic encryption. And the thing is this, each paper has its own PRBG, each paper has its own chaotic map. So this generates a very obvious question. Okay, uh, what if I take a specific PRBG that you have already tested on a one chaotic map? Okay, so what if I change this map and use another one? Will this PRBG still be statistically random? Okay, how will it behave? So the open problem that we're trying to address here is this sort of comparison work where we take one specific pseudo-random bit generator and compare how it behaves under using a collection of different chaotic maps. This has not been done before. I think it's one of the first works that does it. And it is a very, very analytical work, okay? And to do this, we considered a very classic design for a random bit generator. This uses some very classic techniques that you'll find in other papers in the literature. So the idea is this. This is the rule. Xi, if you follow my mouse, is the value of the chaotic map. So we take this value, we multiply it by a very big number, 10 to the d. Here we got 10 to the 10th. Okay, so basically we move the floating point of the number xi to the right. Okay, we take the remainder operator. So this is the cutoff operator. This is non-invertible. Okay, so we basically discard all the significant digits of the map, and we only keep the less significant, which, as you can understand, the less significant digits are the ones with the higher randomness. And then we take this floating point number, 0 point something, and we map it by multiplying it to a number 2 to the z. Here we take 2 to the 8th, so we multiply it by 256, and we take the floor operation. So we end up with an integer between 0 and 255. So we basically generate a byte in each iteration. Okay, so this is a pseudo-random number generator. But afterwards, we simply take the transformation from integer to binary, which transforms it into 8 bits per iteration. Okay. So here this table shows the non-invertibility or invertibility of each action. So we start with the value xi, which let's say lies in a domain x. We multiply it by 10 to the 10th. Okay, so the domain gets, as we say, this is sort of an expansive operation. We expand the domain. Okay, a blow-up operation if you like. Okay, then we take the remainder operation with 1. So we are cutting off the most significant digits and take actually a value between 0 and 1. Okay, and then we multiply this number again with 2 to the 8th. So from a number between 0 and 1, we actually take a number between 0 and 255. And then we take the floor operator. This is again a second cutoff operation, which is not invertible. We cut out the floating point after the dot. Okay, and we end up with an integer between 0 and 255. So basically, this PRBG utilizes two non-invertible operations. The first is the remainder operator, and the second operator that is non-invertible is the floor operator. Now, in the paper, we have a very analytical description of how this prbg behaves against brute force attacks. I encourage you to read the paper. I'm not going to go in depth in here, but we have a very big analysis about how this prbg can actually be resistant to a significant extent to brute force attacks. Okay, so let me show you a graphical interpretation of this. Let's say we have an xi number, 0.12345 up to 16. These are the digits of the decimal part, okay? So we take this number, we multiply it by 10 to the 10th. So basically we move the dot 10 points on the right, okay? So this is the result after the multiplication. Then we take the remainder And as you know, the remainder, which is basically the modulo operation, we discard all the first 10 digits. So basically, we discard all the most significant digits, and we are left with the less significant digits, which are actually much more random. Okay. And also, so basically the point here is this. We first discard some information to increase security, so this is non-invertible. And also we are using the least significant digits, which are the most random ones in the value of the map. So then we multiply this value with 256. So we obtain a floating point number between 0 and 255. And then we cut off this operation. We have the cutoff operation, which only keeps the integer part, and we are left with a random integer. Okay, so this is a visual interpretation of how the prbg works. Now, what we did is this. We did a very, very big analysis. We considered 30 different chaotic maps, so it was extremely analytical. So we took 30 different chaotic maps and we tested how the prbg behaves when we are using these maps as a randomness source. Okay, so we tested statistical behavior, we tested key space, operations per bit, and also speed. And we have very, very good results. Why do we have good results? Because, well, as you see right here, with blue, I have denoted all of the maps that passed the statistical tests, okay, the niche tests. And you see that almost all the maps, with very, very few exceptions, managed to pass the statistical tests. Okay, this is a very positive result because basically it tells us that this chaotic prbg can be generally very, very efficient under many different chaotic maps. So this is the first very good result. Okay. We also found out that most of the maps that we considered have a very big key space. Okay, and also we tested the speed for this generator, and indeed we found out that many of these maps have a very good speed. So we're testing, for example, the very low, very lightweight maps have very high speed. For example, the logistic map has 48 megabytes per second, which is a very high speed, but other maps have also good speeds. We see here 22, 17, 35, 20, 14, 19, 18, 16, 20, 14, 16, 20, 18. So you see the megabytes per second is very, very good in most of these maps. Okay, this is very comparable to other state-of-the-art works. Okay, so this is a very, very nice prbg. Okay, and this is of course a very analytical comparison. And after we did this comparison, we managed to gather some sort of observations that me and you and everybody else can use in any future work that designs prbgs. Okay, so let me give you these 10 very important observations. Okay, well, first of all, the first very obvious and important observation is that the hash function should only use some partial information from the map's value. The idea behind that is that we want to have a non-invertible hash function. This will increase security significantly. Okay, so the hash needs to be non-invertible. So some information from the chaotic map must be discarded. Okay. Secondly, regarding the hash, well, it should be designed in such a way that it negates any statistical bias in the chaotic time series. Now, as you know, chaotic solutions from chaotic systems are generally statistically biased. Okay, so the prbg that you are using needs to break this bias. Okay, it needs to destroy the bias. It should be properly designed to do this. Okay. Now, third observation. As a general rule, we found out that maps that have a higher complexity, okay, are generally better in generating statistically random prbgs. Okay, but there are exceptions to that. So if you're thinking that, okay, Lazarus, I'm going to take a much more complex chaotic map and the prbg is going to work. No, not necessarily. We found out that there are exceptions to that. Okay. So the fact that you are taking a much more complex prbg doesn't mean that you are certainly going to have the statistical randomness. Okay, it's not sure. Fourth observation. Of course, we need to have a very high key space to resist brute force attacks. But also it is very, very essential that we are using maps that have robust chaos. Robust chaos means that in a specific parameter region, we are not having any periodic behavior at all. Okay. These maps are very helpful, very sought after in practice, because basically they tell us that within a specific time region, within a specific parameter region, I'm free to choose whatever parameter I want. So this are facilitating, key management, very good key management. So they are very sought after. Fifth observation, okay. There are some maps that we observe that pass the NIST tests, but they don't have enough key space. That's not a problem. We can use them in other applications that are not relevant to encryption. Okay. So if you have a map that doesn't have a high key space but is statistically random in the prbg, just use it in an application other than encryption. Okay. So there is a solution. Sixth observation, we saw that some non-linearities like the modulo and trigonometric are generally much more effective, okay, in having a good prbg, but they're computationally heavier, okay. So this gives us the seventh observation, which is basically that the operations per bit ratio, which means that how many operations I require to generate a single bit, this is a very nice, a very cool indicator, but it's not directly correlating with the speed. And this is because some operations have a higher complexity than others. So for example, 10 additions may actually be faster than using 3 trigonometric functions or 3 modulo operators, because these operators are much slower, compared to a simple addition. Okay. So different operations have different execution speed. Okay. Now, again, regarding execution speed, if we are using a higher dimensional map, because we considered both 1D and 2D maps, now 2D maps generate twice the number of bits in each iteration. Three-dimensional maps generate 3 times the number of bits per iteration. This is a good thing, but unless the map is lightweight, maybe you're not gonna gain anything. Okay, because if the map has a lot of trigonometric and modulo functions, it's gonna lose in execution time. Okay, despite the fact that it requires less operations. Okay, less iterations. So another problematic thing that we observed, it has probably to do with roundoffs, is the fact that some maps that we used have a very high Lyapunov exponent, the theoretical Lyapunov exponent. But despite this fact, the statistical testing fails. Okay. So although you may be using, as I said earlier, some map that we have studied theoretically and gives us a very high Lyapunov exponent and gives us a very complex behavior, maybe due to roundoffs, the bit generator will fail. Okay. So overall, the idea is this: the performance of the generator will be heavily affected by the chaotic source. So you should, by any means, never assume the fact that if you are having, a complex map, it's going to be good for everything. Okay, it may fail the generator, so you need to test the generator before using any chaotic map. Okay, so these are basically our all observations regarding this work. This is a very analytical work. It is open access, so in the description of the video, I'm going to include a link to download the full-length paper in IEEE access, and also I'm going to include a link for MATLAB Central, so you can download the MATLAB code and generate the bit yourself and experiment yourself. Okay, so that's all I wanted to say, and any questions that you have, of course, you can email us. Please read the paper. I hope you enjoy it, and of course, we're gonna meet in future videos. Okay, so thank you very much.